I'm pleased to introduce a member of our own faculty, Professor Simon Shepard. Many of you know Simon, to kick off the 2020-2021 Jones Seminar Series. Dr. Shepard is an investigator in the SuperDARN network, and he's going to tell us about that network in his presentation today. So I understand this is an array of about 36, maybe more now, scientific radar installations internationally that measure plasma irregularities in the Earth's ionosphere. Very important subject. As a member of this group, he's worked directly with the SuperDARN radar hardware. He's developed new analysis tools for the data. He's published many studies of the ionosphere and magnetosphere using data from the radars, and he's also constructed radars at new sites internationally. Simon is a graduate of Middlebury College and received a Master of Science degree in Mechanical Engineering from the University of Washington before coming to Dartmouth. He received his PhD in physics from Dartmouth, and after an appointment at the Johns Hopkins University Applied Physics Lab, he returned to Dartmouth in 2001 to teach courses and continue his research. So please join me in welcoming Dr. Simon Shepard.
I don't hear any applause, Laura.
Okay,
all right. Sorry, I'm going to share my screen now. Thank you for that introduction, Laura. And let me get set up here. Whoops, I apologize. I have to do one thing here. Okay, one more. All these Zoom things. Okay, so hopefully you can see my slides, and thank you for giving me the opportunity to talk a little bit about my research, which you described a little bit. My research involves ground-based radars, and if you can see this figure over here, these are 2 radars that are located in the desert of Oregon that were built in 2010. I'll talk a little bit more about these as I describe these radars. They're part of this international network that Laura just mentioned. This other figure over here, this is a figure from a recent publication that was published in Radio Science. And it describes a project, a recent project that I was involved in which we used these radars to transmit from one site. In this case, this site is located in Kansas. The signals that we transmit travel up into the ionosphere, and the normal way we use these radars is that signal would then come back to the radar and we'd analyze it, and it would tell us something about the ionosphere that it's traveling through. And so the new capability that we developed was that some of this signal then actually can travel to different radars. In this case, this is a radar located in Oregon, about 2,000 kilometers away. And so we were able to receive and analyze that particular signal. And this is what's known as Bistatic radar operation, okay? So that's really like the whole talk, and I'm basically going to build up to this, and I am going to talk about these particular radars. Okay, so that's one aspect of my research that I'm going to talk about today. Okay, so a little bit of an outline. So by way of an introduction, the acronym for this international network is SuperDARN. It's a network of ground-based radars. I'm going to talk a little bit about that network, what it was designed to do, and how it actually works. I'll use those. I'm most familiar with the radars in Oregon, having built those, and so I'll use those as an example to talk about how these radars actually work. And then I'll show some measurements and some of the studies, in particular some of the studies that were done by students at the Thayer School. The project I'm going to talk about was a recent project. So this is the Biostatic Project. I'll talk about a description of what we actually did, some of the challenges that we had to overcome. I'll show you some of the initial results which were published in that recent article there. And then I was working on this while I was teaching, and so I'll just briefly talk about a connection to the courses that I teach here at the Thayer School. And hopefully I have a little bit of time and I'll talk about some of the ongoing and other new projects that we're actually that we're involved in with these radars. So here's the acronym SuperDARN. It stands for Super Dual Auroral Radar Network. So it's an international network of radars. that are primarily in the Earth's polar regions. So this is a view of the southern hemisphere. This is a view of the northern hemisphere. And these are a collection of radars at various locations. These little pie-shaped wedges, the actual location of the radar is at the pointy end here on the ground. And these little pie-shaped wedges are what we call the field of view of each one of these radars. It's the area in which it makes measurements, okay? These are the Oregon radars, and I just highlighted these in purple here. The other ones are orange. In the northern hemisphere, there's a lot of radars, and so I'm sort of separating them by layers in terms of latitude. These are the lowest latitude radars. They're located at a lower latitude than the other ones. And then we see that there's another layer. So these blue radars in the northern hemisphere, and it sort of corresponds to what's happening in the southern hemisphere. There's not as much land, and so you don't really have much option in terms of where you put these radars in the southern hemisphere. And so these blue radars, this is actually what was the original network, and these are located at higher latitudes in what's called the Auroral region. And that's where this acronym comes from, Super Dual Auroral Radar Network. This was the original network before we expanded it equatorward and poleward. So there's an additional layer there's 4 of them that are making measurements, the observations in what we call the polar cap, okay? So there's, as Laura said, I think she said 3 dozen. There's on the order of 3 dozen radars that are currently operating. They were built and constructed and operated by about 10 countries that are in this collaboration that's known as the SuperDARN network. So before I talk about like how we actually make measurements with these radars and what we're actually doing with these radars, I thought I'd use this analogy of a radar system that's probably more familiar to most people, and that is a weather Doppler radar. So this is a particular animation from some measurements that are made from a Doppler weather radar close by in Albany, New York. And so this is operated here, and it operates, or it works, it transmits signals in the gigahertz range. And those signals travel away from the radar, and if they encounter obstacles, in this case, the obstacles would be rain, snow, sleet, etc., then some of that signal is actually reflected back to the radar site where it's observed. And the more rain, the more sleet, the more obstacles you have, the stronger the signal is. And so you can get a sense of where the intense weather or the storms actually are located here. So it's a Doppler radar. And so if those obstacles, the rain, the snow, is actually moving, then the signal that you receive, there'll be a Doppler shift associated with that. And if you analyze that and look at that Doppler shift, then you can actually infer what the velocity is, or the motion of the obstacles, the rain in this particular case. So this, if you look at the scale, it's actually, so this is about 100 miles, I guess, the sort of scale that we're looking at. And so this is, this is good for local weather, I guess. You can see where it's raining and so forth. But if you actually want to do a study, right, or you want to make a longer term forecast of what the weather is going to be like in any particular situation, or you're trying to understand how these weather systems evolve over time, then you need a larger field of view. You need a larger view of this. And the way you do that is you just combine more than one radar. And so this is a composite image here that has about 100 different Doppler weather radars. So you're looking at data from about 100 different Doppler weather radar systems here. And so now you can start to see, right, the things, you can see these large scale features, and you can see how these storms maybe evolve and are created, okay? And so that's the idea behind our radars. Now, what are we actually trying to study with these radars? Well, and this is just an image from NASA here. And so we're trying to study the connection between the sun and the earth with this. That's what this radar network, the SuperDARN network was actually designed for, okay, primarily. And in particular, what we're trying to understand is the coupling between what's called the solar wind and the Earth's magnetosphere, which is shown over here. So the solar wind is just, it's the outer extent of the sun, which blows outward. And when it gets to, you know, away from the surface of the sun, it's actually basically a bunch of electrons and protons, okay? And we call this a plasma. And this plasma, this wind, blows outward, and when it encounters a magnetic field, in this particular case, the Earth's magnetic field, it creates what we call the magnetosphere. And that's this region here, inside of which there's the Earth. Now, some of the energy from the sun actually couples into the magnetosphere. And it then is transferred along magnetic field lines down into the Earth's polar regions, where these magnetic field lines in the northern and southern hemisphere converge. And so by making measurements in those regions, you can actually infer then what's happening between the coupling between this very large region, which is much larger than the scale of the Earth, and the Earth's magnetosphere. And so that's the reason we actually locate those radars in the polar regions. So the network was designed to study the coupling between the solar wind and the Earth's magnetosphere on a large scale. Okay, so before I talk a little bit about the measurements and look at the measurements, how we make the measurements, let's actually look at what these radars look like. So here's just the fields of view from the two radars that are located in the desert of Oregon here. We have, again, about 35 radars, and we identify them with these three-letter codes here. So CVW and CVE. CV is Christmas Valley. It's the closest town, which is about 16 miles away. And this one looks sort of northwest, and this one looks sort of northeast. So maybe not creative, but CVW and CVE indicate these two radar fields of view that you're looking at here. Now, unlike the weather Doppler radar, we don't have a 360-degree field of view. You'll see why in a minute when we look at the radars. So our field of view sort of is somewhere between 50 and 70 degrees in azimuthal extent. But we see out, in this particular case, we can look out to, say, 4,500 kilometers, okay? And so the fields of view of these radars extend all the way up into Alaska here. Okay, so here's this is that photo from the first slide here. It's an aerial photo of the entire radar facility that's located near this town, Christmas Valley in Oregon. This was constructed in 2010, and this photo was taken maybe a year afterwards. And so these are two radars in the network. Most of the radars are similar. There are some differences in hardware and the geometry, but they all consist of the following. So there's actually two radars here. And these lines indicate, so this is the blue. The blue is Christmas Valley West, and this is Christmas Valley East. The forward direction is where these are looking. Oh, sorry, this is the direction that this is looking in. So each radar consists of two linear arrays of antennas. There's a long array here. This is Christmas Valley West, and this will be Christmas Valley East. And these antennas both transmit and receive signals, all right? And then there's a smaller array, in this case, behind it, and this only has 4 antennas in it. And this is what we call the interferometer array. And so by measuring, this is receive only, and by measuring the difference between the timing that we receive signals on what we call the main array and the interferometer array, we can estimate the elevation angle or the angle of arrival that the signals, from the horizontal, that the signals we actually receive. And so we'll see this in a minute. There's 2 arrays here, and they share a common building, which is shown right here. Okay, we'll look at that in a second. Now, these antennas, it's a phased array, and so the signals that are transmitted from each of these antennas here, they interfere constructively and destructively, and they form what we call a radiation pattern here. And so this is the main lobe, or the beam direction that most of the power is actually going out in, okay? And if you move azimuthally off of that direction, then the power falls off. It doesn't go to zero, and in fact, there's these other little sort of lesser lobes. These are side lobes. And this is just a consequence of the fact that what you get when you have a phased array, okay? Now, we can actually steer the direction of this beam by adding phases, appropriate phases to the various antennas along here. And so we can steer the beam through that 50 to 70 degrees of azimuthal direction that we actually look in, okay? All right, so that's the radar. If we look up a little closer at these, now this is actually Christmas Valley West interferometer, okay? These are the whole site, and there's 64 of these at this particular site, because there's 2 radars, are basically a bunch of aluminum poles that sit on top of concrete piers. And these aluminum poles just hold up the antenna, okay? And so that's what we're looking at. The main array, there's 16 of them. It's about 750 feet long, so it's really hard to get those in a single image here. These poles, if I didn't say, are about 60 feet tall, accessible only by a high lift to get to the top. So the poles are all guyed, and they're guyed with a non-conducting cable. So these are Kevlar guying cables. These are the side guys, which, by the way, were actually constructed, prefabricated by students in my lab in Cummings 216, and then shipped out to the site. So those are the guys, and then here they're also guyed in 4 directions here. So each of these poles is then guyed to the front, where it's anchored into the ground, and then also in the back here it's anchored into the ground. Now these radars, there's this funny little angle thing here that these back guys actually make, and the reason for those is we also have a different type of cable here. So this is a conducting wire, each one of these cyan lines right here. And so this is what we call the corner reflector. These conducting wires reflect our transmissions in the forward direction. And so we're interested in looking in the forward direction. Without these, half your power would go out the back and half would go out the front. And so we have this corner reflector, and that's what what these things hold up, okay? Okay, so again, as I said, these poles, and this is one of the interferometer arrays. So there's 4 antennas. The cyan wires, these are conducting wires. These are the antennas that these poles are basically just holding up, okay? These are horizontal, again, Kevlar supports that we just attach these to. The type of antenna is these are just conducting wires, is what's known as a twin terminated folded dipole. It's a particular type of antenna that has a fairly flat response over the frequency range that we use, which is 8 to 18 megahertz, which is the frequency range that we actually use. And hopefully you'll see why in a second. So the signals that are generated in the electronics in the building, they come through this low loss coaxial cable that's buried in the ground and then comes up and is fed from the center right here. And then the receive path is in the opposite direction. So this is inside that building. It's a relatively comfortable building that we had constructed for this particular project. The Christmas Valley West cables come in through the side of the building on the left, and then the east come in here. These 2 racks are transmitters, 1 for each of the 16 antennas in the west array, and then there's another 16 over here, 1 for each in the east array. Each of these transmitters amplifies the signal. They're capable of generating 600 watts. And so our peak power of what we transmit from each of these radars is about 10 kilowatts. Now I should say that our duty cycle, the time during which when we transmit, right, is only about 1 or 2%. So our average power that we put out with these radar systems is only about 100 to 200 watts. Okay, those signals are generated in some of the electronics in the center rack, which is kind of obscured by this monitor here. There's a very large computer with a lot of cards in the back for creating signals and digitizing signals, et cetera. And then in this, there's several racks right here. This is what we call the phasing matrix. There's a little card which has a bunch of switches and actually physical delays that we add to. This is how we phase the array and steer the beam. Okay, so each one of these is a little card that's attached to one of these transmitters here, and we program the phases into that for set beam directions, and we can step through those beams. Okay, I didn't build, I was in charge of building this radar facility. I didn't build it all myself. I had a lot of help from my colleagues from other institutions. And so here too, I thought I'd show this, right? So here's a postdoc from the University of Alaska Fairbanks. And this is a former PhD student, Ellen at the time, Pettigrew. Sorry, I almost got that wrong. Ellen Pettigrew, Thayer School PhD student. And they helped out quite a bit during this build here. And I'm noticing that Jeff in particular has his feet up on about $36,000 worth of low loss coaxial cable at this point, okay? And just to give you an idea, there was, it's about 7 miles of cable right here, of this type of cable that we had to drag out and then put in those trenches. And it turned out that there was one person that had the correct dimensions and agility while you were dragging out the 7 miles of cable and putting it into these trenches here, very narrow trenches. Occasionally you had to get down in there to unsnag the cable, a very expensive low loss cable, and there was one person who actually could fit into that. And apparently, this is what you look like after dragging 7 miles of cable out in one day. Okay. Okay, so let me now try to explain a little bit let me explain how we actually make our measurements before I show them, okay? So this is actually a numerical simulation. It's a numerical simulation of radio waves propagating in a magnetized plasma or propagating through the ionosphere. Each of these little gray lines is a numerical solution of a ray path. And let me first talk a little bit about the ionosphere, okay? The ionosphere is indicated by the color, and the color indicates the density of the ionosphere. So we talked about the solar wind and how that was a plasma, right? It's a gas in which it's made up of, I think I said electrons and protons, and so it's negatively charged and positively charged ions is what a plasma is. And so the ionosphere is formed primarily by the sun photoionizing the upper layers of our atmosphere. So photons, sunlight shining on the top of our atmosphere, some of that energy from those photons basically strips away those electrons, and you're left with a positively charged ion and an electron. And the gas is so tenuous up there that it can stay in that particular state, and we call that state a plasma. And so in this particular case, now let me just, it's a little bit hard to see these ray paths here. And so I'm going to expand the vertical scale here. It distorts these ray paths a little bit, but I think we can see a little bit more in this particular case. So here's a particular example of the ionosphere. So the radar is located down here in this, in the lower left corner. This is sort of the curvature of the Earth here, and this is range away from our radar, looking in a particular beam direction. And then the color here indicates, this is the vertical axis in altitude above the ground. And so the color here indicates the density of the plasma with this scale over here, which by the way is a log scale. Now, the ionosphere, this is actually a profile of what that looks like. So at 1,500 kilometers, we take a slice through that, and then on the horizontal axis, you plot the magnitude of the density as you go up in altitude. You can actually see that there's a couple of layers here. It peaks about 250 kilometers altitude, and there's a very broad peak here, but there's actually another little peak down here also. And that's sort of the typical composition of the ionosphere. Now, as radio waves propagate through here, as they encounter the plasma, this charged gas, the plasma actually affects that electromagnetic wave that's propagating through there. And it bends or refracts the wave that's propagating through it. And the amount of refraction that the wave experiences is proportional to the density of the plasma. So the more dense a plasma is, the more refraction or the more bending you'll actually get. And it's also inversely proportional to the frequency of the electromagnetic wave that's traveling through it. So the lower the frequency that's traveling through here, the more refraction it actually gets. And so here we are, each of these rays here is a different elevation angle, starting at 0, and I think I'm stepping in 1 degree here up to like 50 degrees. And then I'm numerically solving what that ray path is through this particular plasma. And so what you see are some of these paths here. Now, back to the analogy of that weather Doppler radar, as these signals travel into the ionosphere, if they encounter an obstacle, then some of that power is going to be reflected back towards the radar, okay? And we call that backscatter. So some of that signal is going to be scattered back to the radar, and then you can analyze it. If those obstacles are moving with the plasma, then there'll be a Doppler shift in the frequency associated with that signal that you observe, and you can therefore infer the motion of the plasma by measuring the Doppler shift in the frequency that you're actually observing. Okay, so we're up at 200 kilometers. I know maybe people aren't used to kilometers here, but there's certainly no rain and snow up at these altitudes. So the question is, what are these obstacles? Well, it turns out that there are actually fluctuations in the density of the plasma itself. And so I'll use another analogy here. If you think about the surface of the ocean, in particular maybe on a windy day, right? There's waves of all sorts of different scales on the surface of the ocean, okay? Well, the same thing happens in the plasma. There's fluctuations in that density, and those fluctuations can grow. And if they grow sufficient enough, then it will reflect enough power back to the radar that you can actually then observe it, okay? We call these density irregularities, okay? And those are the obstacles that we're scattering off of. So that's the basic mechanism for how we make our measurements. We transmit signals on the ground, they travel up into the ionosphere, they refract. If they encounter irregularities, some of that signal is backscattered to our radar. We measure it, we analyze the Doppler frequency, and we can then infer the motion of the plasma. Okay, you build a whole bunch of these radars, and then you can see what the motion of the plasma is over a large region. Now, one other thing before I move on, and we look at some measurements here, you'll notice that some of these rays here actually bend over and actually come back to the ground. Now, the ground and, using my analogy, the ocean, turns out, is actually a good reflector of radio waves in the frequency range that we're actually using. And so some of this signal actually, right, you get refraction here, it comes back to the ground. Some of that then travels back to the radar where we analyze it, okay? Now, the motion of the ground relative to the plasma is almost zero. So we don't see a Doppler shift in here, but we can see strong signals that are reflected back. We call this ground scatter or sea scatter, okay? And we'll see some of that in a second here. Okay, so here's a snapshot of 1 minute of data from these two radars in Oregon, okay? We were operating, it looks like here, at about 10.5 megahertz. At this particular time. It's nighttime, and you can see the outline of those fields of view, and each one of these sort of little rectangles here indicates a measurement that we were actually able to make. Now, the color here is, which is obscured by this little box here, at least on my screen, is Doppler velocity, okay? With the standard blue shift is towards, in this case, towards the radar, and red shift is away. And so this region right here, what we're actually seeing, right, is basically a westward flow of the plasma. And we can see this, right? So this will tell us that, again, the Doppler is, when we make these particular measurements, these beams on Christmas Valley West are looking sort of in the easterly direction. And so that means that the flow, which is towards the radar, is in the westerly direction. These beams from Christmas Valley West here are looking in the westerly direction. The sense of the flow is away from the radar, and so that's a westerly flow. So we see this broad region of sort of westward flow at this particular time. And then embedded in that is this fairly narrow channel, also of westward flow, but much higher velocities. The scale here is saturated with these particular values. So these flows, I expect, are on the order of 1 kilometer a second, okay? And this is an interesting feature that's caused by other processes out in that large magnetosphere that are actually then imaged onto the ground, and we actually see those, okay? There's some other measurements in this case, and over here there's this patch of sort of like dark red, that's at the lower limit, and you see some grays and some other sort of noise actually in there. Well, this is ground scatter that I talked about. So signals are transmitted from Christmas Valley East, refract back to the ground, it's scattered then back to the radar, right? And it's essentially 0 Doppler velocity. Over here, you'll notice there's one band of it here, and there's another band of it here. And notice as this is only really in the beams that are over the ocean or the sea. And so, as I said, the ocean is a very good scatterer for our signals here. And so, in fact, what we're seeing here, this is what we call one hop. So the signal goes from the radar to the ionosphere, back to the ground. Some of it comes back along that path to the radar, but some of it continues back up to the ionosphere and then back down to the ground again, and then it's got to find its way back again. We call that 2-hop ground scatter. And so here we're looking at about 4,000 kilometers or more as we actually see these types of measurements. Okay, so just to show you, again, I'm sort of talking about what these radars are, you know, the measurements and what they were kind of designed for. And they're designed to basically monitor the large-scale motion of the plasma. Again, it's due to this interaction of the solar wind with the Earth's magnetosphere. And so here's a technique that was developed. The technique is described in these two papers here, where we combine data from all the radars that are available. And so these are the locations. These little dots indicate data from particular radars in the network. So that's the data. And then we combine this with a model, which I'll talk about in a second here. And then we come up with a best fit solution. So we're looking at large scale or a global solution of what the motion of the plasma is. And so this is sort of a little animation of what we have in a certain time. And I think I'm stepping, it's covered up here, but I think I'm stepping by 2 minutes here. Okay, and so this network provides us this large scale view of what the plasma is doing, and we can then infer what's happening in terms of the coupling with the solar wind. Now, one other thing I want to mention about one other thing we can sort of do with this data is you'll notice, like in this region, there's no data, there's no observations. Now that could be because there's no irregularities there. It could be, in this case, I suspect it's because we don't really have any radars in this sector over here. But anybody who's sort of done any fitting to data here knows that you can get a really good fit to the data just by using a high enough order expansion. But be careful where you don't have data, because that solution will just blow up on you unless it's constrained in some way, okay? And so what we actually do in this particular technique, and there's lots of other techniques too, in order to get the best fit solution, we have all the data available, but we also constrain the solution with what we call a statistical model. So we constrain the solution with some average value of what we think that the convection is under certain conditions, right, at that particular time. We basically are sort of filling in the regions where we don't have measurements with our best guess of what it actually is. And so these models have been developed over the years, statistical convection maps, climatological models, et cetera. And I simply point these out because there are quite a few of these developed by Ellen Cousins here and Evan Thomas here. I was going to say students, but Evan is a postdoc. Sorry, Evan. He's now a research scientist. Okay, so let me talk about these. So the original model was just made with a single radar. That was all that was available. And so you basically are looking at what the average convection is doing under certain conditions. And these are just some examples under certain conditions of what the convection actually looks like. It has to do with the coupling in the solar wind. And so you can come up with an average pattern of what you think, right, that actually, what the radar is actually doing. Or it's based on the measurements, but this is sort of the average of what it does if things are in this particular configuration. Another model was developed once we had more radars in the network. And then these three models were developed at the Thayer School here. So the P is Pettigrew. So this is my former PhD student. As part of her thesis, she developed this multi-radar model of statistical convection. She got married and changed her name to Cousins, and so now it's this is and she also, right, then developed another model. And so Ellen was the first one to look independently at data from the northern and the southern hemisphere and come up with independent models. And she was, part of her project was to look at symmetries and asymmetries between the northern and southern hemispheres. And so that was what this model was part of, right? And that's what I showed in the previous one. Most recently, Evan Thomas, as a postdoc, developed a model which used data from all of the different levels of radars that I was showing you. So sometime we just built the radar when Ellen was she helped build it when she was a PhD student. And so that was our first expansion into the mid-latitudes and then the polar radars too. And so as we added those layers, Evan developed a more complete model that includes data from all of the different layers and some other improvements. And so again, these are the papers. Evan is a research associate here. He developed this model as a postdoc. Okay, so that was a little bit, I really wanted to talk about this new capability here, bistatic measurements here. And so this was a project that was funded by the Air Force Research Lab, AFRL. It's a collaboration between myself, Evan Thomas here at the Thayer School, and our colleagues at Virginia Tech. Virginia Tech operates this similar radar, which is located in a town just outside of Fort Hays, Kansas. Okay, this is the site. And again, we built a whole bunch of these sites which have two radars at each site. And so Fort Hays West, Fort Hays East, okay? And so those are those two particular radars. Now, and I should say that Evan and I both helped build this radar too, which is built in 2009, just a little bit under a year before we constructed the radars out in Oregon. So it's a similar design. That's why we picked these two radar pairs here to do this particular project. For the most part, they're similar hardware and similar software, the design of these radars. Some of the other radars in the network are quite different. The measurements are the same, but the hardware is quite different. And so this project, again, funded by the Air Force, was to develop the capability to transmit signals from one of these radars, have it travel into the ionosphere, scatter off of these density irregularities, and our normal operation then would be that to measure that back at the same radar that we transmitted at. But the bistatic capability then is some of that signal then can be scattered along the direction that another radar is looking in. And in this case, these are the radars located in Oregon, okay? And that's the bistatic capability that we were funded to develop. And so this is the reason, again, we picked that. These are the fields of view of Fort Hays West, in the light orange, Fort Hays West and Christmas Valley East. Those are the two bistatic radars that we used. We'll see in a minute here, we chose to use Fort Hays West as the transmitting radar, and Christmas Valley East was the receiving radar. Well, I'll just say it, that small array, which we talked about, which I mentioned, which is used for interferometry, that is working and calibrated at Christmas Valley East. And so we could also measure the elevation angle of the signals, where we couldn't do that in Fort Hays West. Another reason we chose these two radars, they have a nice common, right, the overlapping field of view. There's a large area. And again, these magenta things are just example beams. This is beam 11 from Fort Hays West. This is beam 12 from Christmas Valley East. There's a large region where we have overlapping beams here where we can make these measurements. Okay, that was the reason we actually chose, another reason we chose those radars. So I guess I'll talk about this first. The main challenge that we actually had in this project was timing. So I mentioned that our duty cycle is 1 or 2%. The pulses that we send out are only at most 300 microseconds. And so we're only transmitting about 1 or 2% of the time. And so the timing had to be such that we needed enough overlap between the two sites such those pulses overlap so that we could actually analyze the signal properly. Regular computer timing is not sufficient. And so we were actually able to achieve sufficient timing using GPS triggering. So each site has a GPS clock in it in the computer, and it generates regular trigger signals that we then use in our electronics to do all the things we need to do to set up the transmission sequence and that sort of thing. So these GPS triggers, we actually so we're able to do this and look at these, and we achieved synchronization between the two sites within plus or minus 5 microseconds. And so that was enough of an overlap so that we knew we would hopefully see these observations. This is just showing you this is showing you that, not the pulse sequence, this is showing you the number of sequences. So we actually send out these pulses, and we send out multiple ones. This is the number of them. So on the order of 20 of these in a 3-second period. So we'll be looking in one direction for 3 seconds, and then we're sort of integrating or averaging the signal that we actually get over that particular time. The top here is the 2 radars at Christmas Valley, and the bottom are the 2 radars at Fort Hays, in Fort Hays. And so there are issues, right? There's 2 independent radars and 1 computer in Fort Hays. There are 2 radars and 1 computer in Oregon. Each of those computers had to control those 2 radars, but they also had to be synchronized between the 2 different sites. And that was probably the biggest challenge that we actually faced. Now, I'm not seeing anybody. There's nobody in this room. I don't know if anyone's listening. But Evan will confirm this, that I was perhaps the biggest skeptic of this project. I didn't think we were going to see anything. I thought it was too complicated. The ionosphere was too variable. It was too hard. We weren't going to see anything. So I was really pleasantly surprised when we actually saw our first bistatic measurements, and these are some of those measurements. We ran a bunch of campaigns where we just operated in this particular mode. We ran this for several months. We picked a few days that we were allowed to do this. And so we ran that, we were successful. And so here I'm showing you some of the data from those first campaigns here. It's a little bit different. First, I'll tell you the color here is power on a logarithmic scale. So this tells you the more red it is, right, the stronger the signal is that we actually receive. Okay, so I'm looking at what we call power in this particular case. This is 24 hours of data, so the horizontal axis, it looks like it's a little bit cut off here. That should say universal time down there. So there's 24 hours of data here. And then this is 1 hour. The vertical dashed lines here are 1 hour, okay? On the vertical scale here, this is range gate. And so our pulse width, which I said was 300 microseconds, determines what your range is, like how far that signal will travel. 300 microseconds will actually travel at the speed of light. So our range resolution is about 45 kilometers. And so we're looking out to about, 2,500 kilometers right here for scale. This is just range gate number here. So here we're looking at only one beam. Okay, and so every 1 minute, right, we'll scan through the entire sequence of beams, and then right, so every minute, each beam is sampled. And I'm just showing you here, beam 13 from Christmas Valley East. And this bottom panel is beam 12 from Fort Hays West. And so what you're looking at in the bottom panel, so Fort Hays West was the transmitting radar. It was transmitting, but it also was receiving its own signal. So we call this monostatic operation. So it's the radar sends out the signal, it scatters off of stuff, and then it measures its own signal. So this is normal operation, okay, down in this bottom panel. I'm just showing you this. And here's the scatter that we actually see from various things. The top panel is a beam from Christmas Valley East. Now we only set this to receive signals, so it was not transmitting at all. And so the signals you're seeing were actually transmitted from Fort Hays West. We did all sorts of tests. You know, we turned things off, turned things on to make sure we weren't picking up anything. So these signals that you see here all originated from Kansas, okay? We received these in Oregon at Christmas Valley. Now you'll notice there's a lot of variability in the power that we actually see. The primary reason for that is this color scale up here, which I realize I just cut off the color scale. So we were running an experiment where we were transmitting for 1 hour at one frequency, right? We were operating at a single frequency. I think purple is probably in the 10 megahertz range. Blue is probably in the 11 megahertz. This is, I think, 14 and then maybe 15 or 16 orange. So we would operate at one fixed frequency for an hour, and then we would switch to another frequency, and then switch to another frequency. And so that's primarily what you see when you see these abrupt changes, right? It's a shift in the frequency. Another big source well, this is to indicate, this is nighttime over here, and this white is daytime. So the ionosphere, when the sun turns on, or at nighttime, right, when it turns off, the ionosphere changes dramatically by orders of magnitude. And you can see the difference in the scatter you get here, right, from what you see at night. That being said, there's still, within an hour, you can see like quite a bit of variability. And that's the stuff we're actually interested in understanding, okay? Here, this was just a proof of concept, but ultimately we want to be able to understand that. It's caused by the ionosphere, and we want to be able to extract that from our measurements. Okay, so here's a schematic from that publication here. It turns out we actually saw 3 distinct modes of bistatic propagation during those campaigns, and they're illustrated right here. So here's our site in Fort Hays West. We're transmitting signals. The first mode of propagation is these red lines, right? These solid red lines. The dashed ones are projection onto the ground, just so it's a little bit easier to see here. So these red lines are what we call the direct mode. And here, we're just transmitting the signal here. It's refracting in the ionosphere. There's no scattering, and it's just coming back down to where we receive it at the other radar. Okay, no scattering involved in that. There's actually 2 traces that we observed. And if you go back to, if you remember what I talked about the ionosphere, the formation of that, there's typically 2 layers. And so we actually think, and this is an ongoing study, we think we observed simultaneous transmission paths through 2 different regions of the ionosphere. The two other modes, the blue one here, these involve scatter, and the scatter location is the solid dot right here. So this is the equivalent of ground scatter. We call this the bistatic ground scatter mode. And so here we transmit signals refract in the ionosphere back to the ground. Now some of that signal comes back to that Fort Hays West radar. We saw that in the previous, the bottom panel. But some of it then is scattered back along a separate path in the direction that Christmas Valley East is looking at. Bistatic ground scatter mode. And then there's an ionospheric scatter mode, a bistatic ionospheric scatter mode. And this is what we were really interested in seeing, right? So we transmit signals from Fort Hays West. There's if regularities are present in the ionosphere up here, some of that signal comes back to the transmitting radar, but some of it goes down along this reception, right, to this receiving other radar here located, in this case, about 2,000 kilometers away, okay? So we saw those different modes, and now I'm building up to that last slide here. And so the way we look at this data typically is we look at it in a two-dimensional sense. I know I'm sort of projecting this in a three-dimensional sense, but we typically look at it in a two-dimensional sense. And so here's data during one of our campaigns, and you'll see that feature. This is that sort of narrow, the scale's a little different. This is a much weaker feature than the one I showed. But this is data from the three radars that were operating. Aside from being synchronized with the radars in Oregon, they were operating in the normal manner, right? This is what we call monostatic. And so that's what you're seeing here, a general westward flow that we're observing in those three radars. The bistatic measurements then we're showing here, this is from Christmas Valley East, and I'm highlighting these with these yellow outlines. Otherwise, it's difficult to see because they overlap. So these are signals that were transmitted from Fort Hays West, did something, and then we actually received them in Christmas Valley East. So there's a bunch of different ways to look at that. And one thing you'll notice, and I'm sort of like stepping through these beam sequences that we used when we made these measurements, just looking at the Fort Hays West and the Christmas Valley East radars, you'll notice that the beams sort of intersect primarily along this line here, which is the bisector between these two radars, okay? That's the distance between these two radars. And those measurements, they occur when the radar beams bisect, but they also overlap this region of monostatic observations, this narrow channel. That's where we see these particular bistatic measurements. So in order to understand that, right, one, obviously then the natural thing to do is you simulate it, okay? And that's what this is, okay? This is a numerical simulation. We call this ray tracing. We saw this before, right? So here we're transmitting radio waves through an ionosphere. Now this is a model of the ionosphere along this beam direction at this particular time. So we transmit, we numerically solve for these ray paths along here. There's two things I've added to this to this figure right here. The first of these little black segments, and those are the locations where those irregularities are likely and the signal would be scattered back to the radar. It's a separate calculation, but think of those as the locations where scattering might be possible, okay? And then I also highlighted a group of these rays here in white here. Those are the rays that those little black segments, the location of where those irregularities are likely to occur, they happen, right? Those are the rays where those irregularities occur, and it's coincident with the intersection of the two beams, okay? So in this case, we're going along Fort Hays West, and it happens where it intersects the beam of Christmas Valley East, okay? You can do the same thing from a different direction, and you'll notice the ionosphere, if you look closely, is slightly different. So this is a different ionosphere along this particular path. Same thing here, and these are the group of paths here that again travel from Christmas Valley, and these irregularities occur at this intersection of these two beams. And so this is the numerical simulation that was developed in order to confirm that these measurements that we actually are observing, that this is what is likely to be happening, okay? That's a demonstration. It's a numerical simulation of the situation that we actually think is happening. So here you're seeing data plotted that was actually collected by these radars, and then on top of that, you're seeing this numerical simulation that supports the idea of this bistatic ionospheric scatter, okay? Okay, and that was the final figure, or the first figure, right? And so that's where that actually comes from. And I just have 2 more slides here, so I think I'll be able to get through this. I wanted to make a brief connection here to some of the things that, well, the classes that I teach at the Thayer School. So it turns out I was actually working on this, developing the simulation in this figure last winter, right before the pandemic hit the US at least, and I was teaching Engines 20. And so as I was developing this, I thought this would be a great sort of wrap up, and I ended up showing this figure, and we talked about it for probably 20 minutes. I showed this figure as my last class as kind of a summary of the things that students could do. So the idea when I was writing this, of course, right, our radar operating system, it's a customized collection of C programs that we've developed over the year. In Engines 20, students learn the C programming language. So all that timing stuff we did, I actually showed some of that code, and fine, there's some fairly sophisticated stuff, more sophisticated than we teach in Engines 20, but they could appreciate it, right? It's the same language that they actually learn. So there's the radar operating system. Data processing, we collect terabytes of data with this network. They're saved to files. The files are then, transferred. And then if you want to do anything with that data, that involves opening files, reading those files, analyzing the data, doing stuff, and maybe making other files. And that's what students learn in Engines 20. So they fully appreciated that sort of thing, okay? Plotting, in MATLAB, students learn how, it's a big part, plotting curves and then plotting 3-dimensional things. And so when they saw this, right, they were like, oh, okay, that's a 3-dimensional plot. And sort of figure out, we talked a little bit about how you might do this, but they could certainly appreciate this. And then the last thing was this sort of numerical analysis, right? The students in Engines 20 had just finished, it was the end of the term, and they had just finished an assignment where they solved a coupled system of differential equations to follow the path of an object. Now it wasn't an electromagnetic wave, but it was, I don't know, it was a basketball or something, using air resistance, something like that. But they solved a coupled system of differential equations, first order differential equations. And so when I told them that's all this was, right, they totally understood that calculating these rays, okay? And so that was that. Now in Engines 20, they used Euler's method. And if I could see anybody out there, if anybody is out there from Engines 91, the other course I teach, and I'm teaching right now, right, they're probably rolling their eyes about Euler's method. And so obviously, right, you're correct, right? You use a more sophisticated, like, adaptive step size, RK45, something like that, right, in order to actually calculate this. But you definitely write it in C, because it's got to, you're doing a lot of these calculations, and it runs, at least 10, if not 50 times faster, right, written in C. Okay, so anyway, that's showed this in Engines 20, and I thought it was a good wrap up to the whole thing. So my last slide, I just really quickly go through this. So in terms of the bistatic, it turns out we actually did a whole bunch of things where we actually did non-symmetric beams, where the beams that were for the transmission and reception leg were not symmetric, and we can learn a whole bunch about the plasma in that particular case, but we still have to figure out how to analyze that situation. I mentioned that direct mode, we had this sort of splitting of those two regions. We're trying to understand that, so I'm doing some simulations of that to try to, that's ongoing work. And then ultimately, right, this bistatic stuff is what we want. It's going to help us specify the ionosphere, okay? And so that's part of what we're going to continue doing is understanding those variabilities. of the variations that we actually see in the measurements to help specify what the ionosphere actually is doing. And so I should say that as a separate but related project, Evan Thomas actually has a proposal to the Air Force in order to do what's called sounding. And so here you're varying the frequency, using the frequency to look at different parts of the ionosphere. And so that's something else that's related, but I got it under Bistatic. It's sort of just related. Another quick thing here is Laura actually said something about me developing radars in, I think, internationally, I think. So true, but so this is a long story. I don't have time for this. So it turns out that there is another radar facility that was originally going to be built in the Azores, but then got moved to Ireland and has now been moved to Iceland. And I will say there actually is physical stuff in the ground in Iceland, although it's been delayed for obvious reasons. Okay, so there's another facility going to be built in Iceland. And I'm hoping, right, being the big skeptic that I was of this whole bistatic stuff, first thing I'm going to do when those radars are on, I'm going to do bistatic measurements between Iceland and Oregon. Okay, that's 6,000 kilometers. And I did some the other day. I was looking at this. It's going to take 6 or 8 hops in order to get there. Okay, but I think we'll see it. There's other instrumentation that are in the fields of view of these Iceland radars, particularly in northern Scandinavia. They have a lot of instrumentation, and so we'll be able to do a lot of science with other instruments, okay, not just the radars. One other quick thing we can do, so actually it's a current project that Evan Thomas is running here, so we can actually determine boundaries of sea ice using these radars. And so he's developing algorithms to sort of do that on a more regular basis. And then the last thing I'll say is we have a big, I say we, my colleagues that operate these US SuperDARN radars, we have a big proposal into NSF to upgrade our radars to do imaging. So we'll basically put a receiver on each one of those antennas and be able to do radar imaging, as well as, I hope, run multiple channels so we can actually be doing some of this bistatic simultaneously with the other stuff that the radars were designed to do. Okay, so sorry, I think I went a little bit over, but that's my last slide.